fit with. I stuck in 2 extra questions, but I'll do them anyways now. So what I didn't give you last week, which isn't too difficult, I wanted you to get the unit of PV without using the formula from the lesson. Okay, so let's see, the dimension of PV is equal to dimension of P multiplied dimension of V. What's the formula for pressure? Force over area, and for volume it would be, x, y, z if it's a cube. Okay, what is the, so if I look at the units now, what's the unit for force? Newton over meter squared, and here x, y, z, or volume? Meter cubed. So what does this simplify down to? Newton meter, which is the same as what? So remember the unit for, remember what the formula for work is. It's force by distance. So the unit, what's the unit for work? How do you measure work? Joule. And what's the unit for force and distance? Yeah, so a joule is the same as a Newton meter. So here, joule. So in other words, this here has the same dimension as work and energy, i.e. units of joule, yeah. But this shouldn't surprise you, because in the lesson, what did you learn PV is equal to? I think it was 3 over 2 times the energy in the gas, the kinetic energy, right? So the result shouldn't surprise you at all. Okay, write this one down. I've seen this one in the exam, by the way. It's a small 2-mark question. This one just like this, yeah. Got it? Yeah, can I do the next question? Okay. Estimate what the pressure on an airplane flying at roughly 10,000 feet is. And I said feet is, about 3 feet is 1 meter. And the reason I use feet is because if you were in an airplane, I think this is what the pilot says, I think pilots measure altitude in feet. Yeah. Okay. Okay. So here's our Earth, and then here's our air, and then here's our plane. And this distance here is about 3,333 meters, about 10,000 feet. So the pressure here at this point, what's the formula for pressure? Rho GH. This is the one I meant to use. Do you know the G here? Yes, of course. Do you know the density of air? Yeah, I gave it to you already. It's like 1.3 or something like this, isn't it? Do you know the height?
Yes.
What is it? No. No. It's not. It's not. Because remember, you measure downwards, not from the ground. You measure from the top of the liquid or gas downwards.
Right.
That's the formula we did last time.
So you can't use that from the ground.
No. Our formula was from the top down, not the other way. So we have to find the H here. Now, what did I say the thickness of the atmosphere was? Was it like 8 kilometers or something?
Yes. Yeah, 8.5.
Well, 8.5 was it?
Approximately 8.6.
Okay, we'll just say 9,000. Okay, so we'll say 9,000 minus 3,333. That's the height. So this will equal 1.3 times 9.81 times 9,000 minus 3,333. So you get an answer of 72271 kilopascals. No, not kilopascals. Pascals. Or if you want kilopascals, that is 72.3 kilopascals. Now, do you remember how much one atmosphere was? I think it was 101.3 kilopascals, is that right?
Yes.
So if I convert this into atmospheres, which I would like to, you get here 0.71 atmospheres. Now the reason I convert it into atmospheres is to try and help you understand how big this is. So at ground level, what's the pressure on us right now from the air? It's 1 atmosphere. So as you can see, as the plane is flying at 10,000 feet, the pressure on the plane is less than this, 0.7 atmospheres. And if the plane could go all the way into space, what would be the pressure on it from the atmosphere? Zero. Okay? So it's not surprising you that this is decreasing as you go up. Okay? So you can see that it's about 30% less pressure, we estimate, at this flight, at this altitude. Okay? So 0.71 atmospheres of pressure. Okay, have you got that? Yes? Yes? Okay. Let's have a look at the next one. Why doesn't the ideal gas law work for water as a liquid and a solid? So why doesn't the ideal gas law, why can you not use the ideal gas law firstly for water? So do you remember with the ideal gas law you said that there must be the particles must be far apart, not interacting much, occasionally colliding. So why does it not work for water?
Because that law.
Yeah, the water, the biggest problem I think is that the molecules are very close together. And the density is not small, you know. Okay, what about for water? So that's water as a liquid. I don't need to write that. Okay, so what's the big problem with ice? Well, again, the molecules are not very close together, but close together. And any other problems? The density is not small. And there's one more big problem.
Molecules are indivisible.
Yeah, so they're not even moving around hitting each other. The molecules aren't free. Okay. You got this? Yeah? Okay.
Mm-hmm.
Yeah? Yep.
Alright.
Okay. So a building is 100 meters tall with a 10 by 10 base. Take the density of air to be 1 kilogram per meter cube. What is the difference in air pressure between the ground floor and the top floor? Okay, so, sorry, what number is this? 4. Okay, so what you need to picture here is you have your building and it's 10 by 10, so the area here is 100 meters squared. And then on the bottom it's the same, 100 meters squared. And I think I said here this is 100 meters. Yeah. So do you remember the formula for density is, sorry, pressure is rho g h1, and I'll call the first height here h1, and then the bigger height here, more pressure, h2. So pressure on the ground is rho g h2. So how much of a difference? What's the difference in the pressure? So that's P2 minus P1. So it would be the bigger density, sorry, the bigger pressure minus the smaller pressure. Which will be rho G H2 minus H1. Now look, although you don't know what H1 and H2 are, you do know what H2 minus H1 is. What's that? H2 minus H1?
100, yeah.
100. So I told you to take the density to be about 1, so that's gone. So it'll be, the difference will be about 100 G, which will be 981 pascals. So roughly 1 kilo pascal. So that means if the pressure down at ground level was 1 atmosphere, 101.3 kilopascals, then up at the top of the building, what would the pressure be? 100.3 kilopascals. That's a noticeable difference. You could actually easily measure that. In fact, some phones have a, oh, I didn't actually tell you this. What do you call the machine that measures pressure?
Pressure meter.
An amazing guess that, believe it or not, is wrong.
Manometer.
Barometer.
Barometer.
Some phones have a barometer in them, and the barometer is accurate enough to measure your height to the nearest meter. So when you move your arm up in the air, the pressure drops very slightly, enough that your phone can calculate your height.
Yes, 100. Wait. So this one is writing in MP.
Oh, you have pressure on your phone?
Yes.
Can you change the unit to pascals?
Hold on. Let me see.
It's in millibars, is it?
Yes, millibars.
Can you change it?
Um,
No, that's okay. Tell me, what's the pressure right now in millibars?
1004 points. Wait. 1003.4.
Wait, that sounds like it's in pascals.
No, millibars.
Okay. What's what's the unit? MB?
Mm-hmm.
Big case? Low?
I think it's all them big case.
Both big?
Yes.
Maybe I can put it in atmospheres. Dude. I'll just go to this conversion chart. Alright, what did you say the millibars were? MB was 1003.4. So that's 100.3 kilopascals. So the pressure right now in this room is 100.3 kilopascals. Slightly lower than 1 atmosphere, which means the weather is turning bad. True. And when the weather gets warmer, it's slightly more than 1 atmosphere. So, as you can see from the wind trying to get in, yes, less than 1 atmosphere seems about right. Okay. Number 5. What is the kinetic energy of the air in a 30 centimeter wide balloon? Okay. So you have a balloon, it's about 30 centimeters wide, and there's air inside of it. I don't tell you the pressure. Well, I'll ask you now in a second. The formula is PV equals 3 over 2E. So E equals 2 over 3 PV. Now, anybody want to have a guess at what the pressure in the balloon is? It's not going to be less than 1 atmosphere, because if it was less than 1 atmosphere, the air would compress the balloon. It could equal 1 atmosphere, or it could be most likely greater than 1 atmosphere. No, I reckon it's equal to roughly 1 atmosphere. It's not going to be too different to 1 atmosphere. So we're going to approximate the pressure as 1 atmosphere. And remember, the formula for volume is 4 over 3 pi r cubed. So we get energy is 2 over 3 times 101.3 kilopascals times 4 over 3 times pi times r cubed. So the energy, the kinetic energy of the air molecules in the balloon is 2 over 3 times 101.3 times 10 to the power of 3 times 4 over 3 times pi times 0.3 power 3. You get 7637.8 joules. Or if you want, that's roughly 7.64 kilojoules. Yeah. Okay, one more question. Yeah. Yeah. Okay, so the last one here. There's a gas cylinder with radius 3 centimeters and length 10 centimeters, and the pressure is 3 atmospheres. A mechanical arm pushes down on the cylinder and reduces its length to 5 centimeters, while its pressure was increased to 7. So let me just draw what's happening here. You've got something like a piston. I think I said the radius was 3 centimeters. And then the height here is 10 centimeters. And the pressure inside here is of 3 atmospheres. Then what happens is an arm pushes down on the cylinder. So now like an arm, like some machine pushes down on it. So now the pressure is only 2 atmospheres. but the height, sorry, not 2 atmospheres, what am I saying? 7 atmospheres of pressure. And the height now is 5 centimeters. So the question I want to know is how much work was done by the arm. So let's calculate the energy here and the energy here. So E1 would be 2 over 3 PV, which would be 2 over 3, 3 times 101.3 times 10 to the 3. That's the pressure. And then the volume is pi or squared H.
Three times what?
Here,
Yeah.
2 over 3.
No. 3 times 10.
101.3. It's an atmosphere.
Okay.
Yeah.
Why do you use pi r? Oh, it's a circle.
It's a cylinder.
Oh.
Right. So this here is 57.28 joules. Now in the second cylinder, if you do the same thing, except just change this to 5 centimeters, and the pressure is now 7. So if you just use the same formula but change the numbers to 7 atmospheres and 5 centimeters of height. Oops. It is now 66.83 joules of energy. So where did the gas get this extra energy from? So the gas, when it went from here to here, got extra energy from the arm. Therefore, that's how much work the arm did. So the work done was 66.83 divided by, minus 57.28. So that is about nearly 10 joules of energy.
That's by the arm.
By the arm. Not only do I know how much work the arm did, I can even know what was the force the arm required to push the gas down. Because what's the formula for work? Force multiplied distance. Now you know what the work is, 9.55. Force we don't know, and the distance we do know. The arm moved down. How much did the arm move down? 5 centimeters. So the arm exerted a force of 191 newtons on the gas to compress the gas to half its size. Question, KJ? You're confused, shocked, or mesmerized? Which is it? None of those?
Yeah.
You sure?
Yeah.
Alright. Okay, let me just close this. Actually, I can stop this recording. Sorry, do you have this written down?
Yeah.